Hello, everyone. So we have another MATHCOUNTS problem. So this was a target question number 8, so which is the last question, so meant to be the most challenging one. And we have a polynomial and has a positive integer coefficient. So usually this doesn't really matter, but we are told in the problem the integers like coefficients are positive, which is something we are given to should be used. And P of 60, when you plug 60 into this expression, we got a perfect square. So that's another information, but it doesn't really give us much because if you plug 60 for x, you will get 60 squared plus a times 60 plus b, but you never know ab, so which is why it's not really obvious what to do with that. And the equation has two different integer solution. And based on this, we're looking for the least value of the value of b. Okay, so it's a challenging question. It looks like nothing is given. We have some like hints like positive integer coefficients. P of 60 is perfect square, and the solutions are different. So, but let's see how we can apply all these together. So since we have a quadratic, maybe we can factor them. So I'm gonna just start with P of x as x squared plus ax plus b. And this could be factored as x minus the first solution. I'm going to name that's root 1. So the solutions are, let's say, the root 1 and root 2, okay? And times x minus root 2. If you know the Vieta relation, you can skip this step, but I'm going to just do this way. And if you multiply these, that will be x times x, which is x squared. X times minus r will be. The reason why we are just doing this, if you are wondering why, what makes this like binomial 0 is r1, right? So x minus r1 has to be 0. If you are looking for zeros or solutions, that means r1 is a solution. If r1 is a solution, one factor should be x minus r1, basically. That's why we just factored this in terms of solution. And that is x times r2, which is minus r2. And then r1 times x will be minus, there is an x right there, r1x. And then r1 times r2, that will be plus r1, r2. If I combine these middle two terms, so we have x term, and then we have r2 and r1 as a coefficient with their negative sign. I will just take that as r1 plus r2 x plus r1 times r2. And this is equal to our polynomial that we are given. Okay, so that is plus b. So if these two are equal to each other, coefficients of each corresponding term should be same. The quadratic term has a coefficient of 1, quadratic term has a coefficient of 1. That is how we actually start, like write this equation without having any number right here, because this was a monic polynomial, meaning that coefficient is 1, so it's easier to kind of factor. And the coefficient of the x term is this middle term, like this number. So that should be same as a. So I will just say a equals negative version of the sum of the roots. And this is my constant term. So r1 and r2 is just two different integer. The product will be a number as well, positive integer or negative integer, it says. Two different integer. So, but the product will be just the product of two integer, which is also number. So that needs to be same as b. So the b is gonna be r1 times r2. Okay, we got this, but no, it doesn't really help much. You can skip all of these steps, like all these steps, if you know the Vieta relation, we can just get this immediately. But we just did that way for those who don't really know about the Vieta relation. What we do now, so we are looking for the b, least value of b, which means we are looking for the product of the solution, basically. Okay, but we don't know the roots, and other information we are given was the positive integer coefficient. So like the sum is just a is the sum of the roots of the negative sign. Like, the product is b. If b is positive, like if this number is positive, so the r1 and r2 should be the same sign, which means either both of them will be positive or both of them will be negative. And But at the same time, if you take these two positive, that will be sum is positive, but there is a minus, a will be negative. But we are told it is positive, right? So which means the roots has to be negative. So I will say from here, just the R1 is less than 0 and R2 is also lesser than 0. This is something. And we want to find the product of the roots. Okay. But also we know P of 60, right? So maybe we should use that somehow. If I plug P of 60, I can plug into this given expression, which doesn't really give us anything more, but I can plug it right here as well because these two are the same thing. So that could be written as like 60 minus R1 times 60 plus R2. And now we are told this is a perfect square. Okay, so, but how this is going to be helpful? We already know like R1 and R2 both negatives, but you know, when you subtract a negative number from 60, like there's a minus right here, like 60 minus a negative number, this become a positive number. So subtracting negative doesn't make much help for some reason. Actually, this is also negative, right? Because as my next step, I will just try to find some plug-in numbers. I just want to kind of deal with the positive thingies. So that's why I don't want to deal with the negative numbers because it might be a bit confusing to see what number should we plug and stuff. So which is why I'll do some sort of substitution right here. So what I mean by that, I'm going to change R1, which is a negative number, with negative version of a solution. Let's say negative version of that number. And then the same idea, R2, I'm going to replace that with negative version of R2. The reason why we are doing, because the product is what we are looking for. B is what we are looking. Just keep that in mind. But if you multiply the negative version of the solution, negative version of the solution, the product is still B. So multiplying these twos is the same as multiplying these two, which doesn't make any difference. So what I'm going to do, I'm going to plug these into this equation. So I'm going to say perfect square. Okay, so perfect square is equal to 60 minus R1, but R1 is negative version of the capital R1. So that will be 60 minus minus, which is plus capital R1. I hope this is clear. And then the same thing with R2, which is 60 plus R2. The reason why I'm doing this, because now R1 and R2 both positive, right? In this case, because R1 was negative, right? And then we just take the negative version of that, so we can kind of make this positive. So now we are gonna get R1 and R2 is positive. Okay, so now we don't know which one is bigger than which doesn't matter. So I'm gonna just take R1 is smaller than R2 and then do some casework. So let's try with that. So the if R1, actually this is capital R, is like 1, right? Then my second solution should be at least 2 because we are told the solutions are like different. So, and then they are integer. So, and then R1 is just the negative version of the solution. So the R2 should be at least 2. So then I will just say let's plug into this equation. If I have the PS, which is perfect square, the short way of writing that, equals, if R1 is like 1, that means 60 plus 1 is 61 times 60 plus R2. And our goal is to get a number for R2, which is larger than 1, that will make this product to be perfect square. So this is kind of trial and error, but at the same time, you can kind of use that numbers that we are given in a way that we can get what we are looking easily without really trying too many stuff. You know, we are going to multiply 61 by the number that we got from this parentheses, and the product should be a perfect square. So if this is 61, which is a prime number, then this number should be a multiple of 61, but also it should include a perfect square, because if I just say this inside is just 61, which means R2 is 1, then R1 and R2 will be equal, but we are told they are different. So we cannot just take the this guy to be 61. We should multiply probably 61 by another perfect square, which is the smallest one is 4. So which is why R2 should be at least, I will say at least, 4 times 61 minus 60. So let's make sure we understand this part. So we subtract 60 because this number, I'm just trying to see what number should I have for this whole parenthesis. The whole parenthesis should be at least 61 times a perfect square, so we can get the result of a perfect square. And then I'd like to multiply 61. The whole thing should be 61 times perfect square, which is 4 times 61. So the 4 times 61 is the inside of the parentheses. But if I look for the R2, then this needs to be crossed. So I just subtract 60, so we can get this inside as 4 times 61 at least. And anything larger than that does also work. That will give us perfect square, but this is going to be the smallest for R2. So in this case, R2, 4 times 6 is 24, which is 240, and 240 minus 60, 180, right? And then there is a 4, so 184. So R2 is at least 184, okay? So then product of the R1 and R2 is what we are looking. So the R1 and R2. R1 is 1, R2 is 184. So that should be 184 at least. So this is the first case. So if R1 is 2, so we are going to kind of use a similar reasoning. So perfect square will be equal to, now we are going to plug like 60 plus R1, which is 2. So 62 times 60 plus R2. And if you get what I'm trying to do right now, then you can just pause and then try to see if you can finish the problem. And that would be great to see. And R2 should be like, this is not a prime number, but that's 31 times 2. So the inside of this parentheses, the sum of these two numbers should be a number that is going to be multiplied by 62 to get the perfect square. So you can say maybe 31 times 4, right? So if you just do that way, the whole thing, 31 times like 4, because, I mean, 30 times 2, not 4, because this is 2 times 31, so I should have 2 times 31, but that's going to be smaller. That will give me 62, or it has to be 62, which we can. We should choose something, this parenthesis, that is larger than 62, so we can get R1. I mean, R2 is larger than R1, because I assume the first solution is R1 is smaller than the second, which doesn't matter if you just do the other way around, but I just use that for our question. So then we should choose something else. In this problem, I multiply by 4 because 4 was the smallest perfect square that I can multiply to get another perfect square. So I can just use the same thing. It's 4 times 62 minus 60. So that means the R2 is 4 times 624, which is 240. And then there's another 8. So it looks like we have 188 in this case. And if you multiply like 2 by 188, so the product is way bigger than 184, so that's not the case. So far, this is the largest one. If I try a few more, okay, so I'm not sure why I'm just doing this. So the R1 is 3. Okay, in that case, the perfect square would be 60 plus 3, which is 63, times 60 plus R2. Okay, and then this has to be a perfect square. 63, like I can try still like 4 times 63 minus 60, which is possible, but your goal is to get a perfect square, not just a perfect square. Your goal is to actually get a smaller perfect square because you're looking for the smallest product. So you don't want to just multiply the like 63 by 4 and subtract 60, even though that will give us another perfect square. But if you can get something smaller than that, you should try, which I do have in this case. So the R3 should be at least, okay, so this is 9 times 7. So 9 is a perfect square. So if I multiply 7 by some other number, that will give us larger than 63, then that looks good number. So I can try that like 7 times 16, because 16 is a perfect square like that you can multiply to get larger than this. So that means we can just try 7 times 16 and then minus 60 for the R3. I mean R2. Okay, so if you multiply that, that will give you 7 times 10, 70, 7, 6, 42, which is 112. If you subtract, so you will get 52 for R2. As you see, this is way smaller than the previous one. So the product of these R's will be 3 times 52, which is 156. It's smaller than this because the R1 is getting bigger and bigger. So if you can get way smaller number right here, you can just get the product, but at the same time, we are getting the R1s is bigger. So keep that in mind. So the R1 is equal to 4, and the result will be perfect squared when you multiply like 60 plus R1, which is 64, and then times 60 plus R2. And the R2 has to be at least, again, we are going to find a perfect square. That will be our result when you multiply by 64. But 64 is a perfect square. So your goal is just to multiply 64 by something. That will give us a perfect square that is as small as possible. That will require that like R2 should be larger than 4. So that's something we have to keep in mind. So you can like use a similar approach, like you can multiply 64 by 4, and then 4 is perfect, 64 is perfect, and subtract 60, which is okay, but you can do better than that because 81 is another perfect square that is larger than 60. So if this parenthesis is 81, so you will get like 9 times 8 to the second power, which is 72 squared for the whole product, which is a perfect square. And then R2 will be a bit smaller number. So, which is why I'll try the parentheses could be 81 minus 60, which is just 21, which is way smaller than this one. And R1 times R2 is equal to 4 times 21, which is 84. As you see, this is so far the best. So, okay. And if you keep doing this a few more, so if you try like 5, 6, 7, 8, or 9, you're going to find some other values and see which one is the smallest, and that will be the answer. And I just don't want to complete the remaining at all, but I'm going to leave that for you. I'm going to do one more. So let's say if R1 is like 5, okay, so then the result is perfect square when you multiply 60 plus 5, which is 65, times 60 plus R2. Okay, and then this is like 5 times 13. None of them is perfect square, so both is prime numbers when you consider. And you want to find a number that will be multiplied to get a perfect square, which means this parenthesis should have at least a 65. If this inside is 65, that means R2 is 5, which is same as the other root, which is not possible. We should have something larger. So which is why we should have the inside of the parenthesis 65 times a perfect square, which is 4 is the smallest one. So I will just take R2 is at least 4 times 65 minus 60. And if you do this, the R2 is just like 4 times 6, 24, 240. And then 240 minus like 6180, but there's 45, which is 20. Let's add 2. That's going to give us 200. But if you look at this one, this is itself already larger than this, and then you are going to multiply by R1. So the product is way worse. So that's not going to be answer either. And if you keep doing this until you get the like R1 is equal to 8, your R2 will be 93 at least. That's possible. But the product is way bigger already than 84. So which is why no other product will give us smaller than 84. So which is why we do get 84. If this is the case on the test, let's say you got a few and then you don't really have much time, and then based on what you've seen is 84 is the best shot, then you can go with that. Because at the same time, you kind of feel that this is getting bigger, the product is going to be multiply by 5, 6, 7 as you go. So which is why if you don't really get too small for R2, which you can, because if you choose, let's say R1 as like 9, R2 should be at least 10 because R1 is smaller. That means 90 already. So which means you are going to try at most all the way to the 9, which is not possible to get something smaller than 84. So which is why if you cannot get anything smaller than 84 until checking by 9, then we are good. And then we don't want to kind of spend time. But this is a question where we need to use our understanding of like factoring, but that wasn't enough. So we should apply like what integer solution tell us, and then what that perfect square means for us and stuff like that. And we just apply all of these like hints to get some relation. So I hope that was clear. I'll see you in the next video.